Wonderful. So, yeah, this has been a great weekend. I really appreciate you letting me come and demonstrate for you. So last night, after the meeting and dinner and everything, I did go back and took a little bit of our mokume bar, something about this length, and I upset it, and we created this little sort of piece of, not quite sheet metal, but thin plate. So we'll just pass this around. And the purpose of doing that just was to show that, at least with mokume that's been well made, you can do a lot with it from a deformation standpoint. Now, as I said yesterday, you have to understand how to do that so that you don't have it either too hot or too cold, that you're using your equipment to have the correct guidelines for what it is you're trying to do. So there's definitely techniques that matter when you're forging mokume, when you're forging anything else. Technique matters, and you need to understand what that technique is for your job, whatever that is. But with the right techniques, we can take that mokume and work it completely against the grain, if you will. And that's kind of neat because it looks different than these other pieces that we did earlier in the day. So that was the point of that exercise. This morning, I have what I think of as maybe somewhat of an ambitious project. We'll see if we can get it done by noon. That seems a little bit ambitious. But I've had pieces laying out here on this corner table all weekend long. These are different steps in the making of a firefighter's tool called a Halligan bar. Some of you, I think, are maybe familiar with the tool. I've got a couple that are pretty close to the final shape. This is probably the closest, and this was not actually fully done, and it's not quite perfect either, but it illustrates a lot of the features that a Halligan bar has. So it's really a modified pry bar. You have sort of a normal-looking pry end here. This, to be completed, would actually have a slot cut into it so that you could get around a fastener or around a door handle or something like that. And you have another prying device here. What makes this tool unique is you have a spike that's coming out at 90 degrees to these other features. We can pass this around. This is a little short. This was the second one that I made, and I made some changes to some of the dimensions of other features and came up shorter than I had originally planned to. I'd already cut my stock to the weight I thought I needed. This was my first attempt. You can see I hadn't finished this end. This end turned out okay, but not quite ideal. And we can pass this around too. This one ended up a little longer. The shaft section ended up a little bit smaller in cross section. Maybe we'll start this one on this side. We'll start this over here, and you guys can pass that around. But what I'm interested in with this tool is how do you make it as a single piece forging with no welding, no riveting. How do you create that all out of one piece of metal? And that's not the only way you could make that tool. Like from a purely functional standpoint, if you needed a Halligan bar, you could make a forging and you could weld a feature onto it and do a good job with your welding. It's a perfectly functional tool. But from a forging standpoint, it's kind of just a neat challenge to try to do it all out of one piece. So what I had to do in figuring out that was have to start with what size you want this tool to be, right? So I said the first one that I passed around is a little short. That's a little bit short for the way the firemen would probably usually use that tool. The longer one might be a little bit too long. And probably each fireman may have their own personal preference. You can find some really interesting discussions of these tools out on YouTube. And so I use those as reference for myself and came up with what I wanted to try to create. And now I have to consult my notes. So give me a minute to get those out. So what I was trying to do was make a tool that was basically around 30 inches or so end to end. And had a shaft section that's a 1-inch octagon. Yeah, so So we're looking for an overall length of about 30 inches, and that dimension comes from the distance between the vertical portions of the door frame. The fireman wants to be able to have the ability to work through that door frame. And then the kind of the blade section, the wide flare to end, is often slid underneath a door. And keep in mind that, I think of a door as like the door of my house, it's a little wood frame hollow core door. But these guys have to use these on steel industrial doors with steel frames. So they need to be quite robust. They might need to be wider or thicker than we would think for, say, taking apart something around our house. So I have a main blade section that's about 6.5 inches long, a shaft section that's 20.5 inches long, and the opposite end where the two forks come out, or the two pipe areas come out. It's about 3 inches from the outside corner to where the shaft section starts. At least that was what my design is supposed to be. And then I have desired dimensions for the width and the length of each of the features that come off that shaft. And I've got a little drawing. I can pass this around. I'll leave that back, but you can pass that around so you can kind of see what I was working to try to get to. So and while I'm talking, I'm going to put a piece of metal in the fire. So this is what we're going to start with. This is a piece that's this is 1 3/4 thick. It's 3 1/4 inches wide. And this one is about 9, I think this is 9.5 inches long. Yeah, just a tape measure here. I'll tell you exactly what it is. This one is 9 1/4 inches long. So this size. How did I come up with this size? You get there by understanding a bunch of different things all at the same time. I'm going to put this in the fire, and then we'll talk about how we figure out those dimensions.
Could you repeat the dimensions on that?
Sure. Yeah, the starting block.
Yeah.
Yeah, it's 1 3/4 thick, 3 1/4 inches wide, and about 9 1/4 inches long. Just realized that I haven't put my safety glasses on this morning, so give me a moment to not be a bad example to everybody. Change those out. So how do I come up with the size of a piece of starting material for a project? And this would be any project, not just this one, but this is a nice one because it's kind of complex. So the first thing that we need to think about is how much weight is required for this job. And the way that we start determining that is understanding the size of the part we want to make. So I just passed around a little drawing that shows what my target dimensions are going to be, right? So I've divided this project into three sections. I have the wide flat section, which on my little drawing I call a blade. I have the shaft section, and then I have the other end of the part. So I've got 3 different sections. The shaft section is the easiest. It's an octagon, and you can calculate the area of an octagon, the length of that section. That gives you a volume, and we know the density of steel is 0.283 pounds per cubic inch. Everybody should remember that. Never forget that. 0.283 pounds per cubic inch. So if I know a volume, I can multiply that times the density, and that will give me the weight. So I can figure out the weight of my shaft section. That's the easiest part of this project because it's uniform. When you get to the next section, so the next section is the kind of this blade section down here. And so this is a little bit trickier because you have a section here. This is 2.5 inches wide. It's an inch thick, but then it tapers over a distance of about 5.5 inches from a 1/2 inch thick down to something probably like, I don't know, 1/8. And it flares from 2.5 to about 3.5 over that length. So now we have something that's tapered in 2 dimensions. That's a little bit more complex geometry. We can do some estimating. If you have so if you have a simple shape, something that's trapezoid shape, if we assume that our trapezoid is a uniform thickness and not tapered, and we want to figure out and assume this is symmetrical and not asymmetrical like I've just drawn it, we can imagine this as a rectangle, right? You can pencil in some fake lines here, right? And you can calculate the overall area. You can take this triangle and this triangle, and if you flip them incorrect and lay them next to one another, they become a rectangle. You can calculate the area of that rectangle, subtract that area from the overall area, and that's the area of what you're left with. That's a good starting point, and you can, if you had a uniform thickness, then you can, area times thickness gives you volume, and then times density gives you weight. We have a taper this way, so you kind of have to repeat that exercise in the opposite dimension, and it's okay to just guess a little bit too. But so that's what I ended up doing. What I found, and the other thing, well, what I decided to do was, I said 2.5 inches wide, 1 inch thick, 4 inches long should give me enough volume to get what I want here. And it actually works out pretty good. One of the things we have to account for in a shape like this being made the way we're going to make this is that we're going to have some metal that ends up bulging out on the end like this here. And in the finished piece, we're not going to want that. We're going to cut that off. So as we come up with our desired starting volume, we have to recognize that there's going to be some loss in certain parts of the job. That's going to be one of those. Again, we're going to have to guess a little bit at what that will be, but you can make some estimations. So my little sheet passing around, I think, kind of gives a breakdown of the sort of the blocky dimensions of each of those sections. You have a similar kind of an exercise to do on this feature here. So this is 1.5 inches wide, about 6 inches long, 1/2 inch thick at its base, and again, it's tapered. It tapers a little bit out in this dimension from 1.5 inches to 2 inch. And then lastly, you have a conical shape that's roughly 1 inch at the base and about 6 inches long. And if you don't know off the top of your head how to calculate the volume of a cone, which I don't remember from high school either, you look it up online, punch into one of those online calculators, put in your dimensions, it tells you the volume. Now you have the volume, you know the density, you figure out how much mass or how much weight you need for this feature, right? So really, if we look at this tool, we have five sections. Our blade section, our shaft section. This happens to be about 1.5 inches square and in maybe 2.5 or 3 inches long. That one is also pretty easy to calculate because it's a square. And then you have this and this, right? So you can break this down into its individual segments and calculate the volumes and the resulting weight that you need to make that job. Except that it will be wrong, it won't work, and you'll come out with a part that's undersized if you do that. Yes, Lee?
Tell me if I'm wrong, but what I've done to go through an estimation of that is take like the center cross-section of the plane, take that point, because we know we're starting to taper from 1/2 inch to 1/8 inch, and what that center point is, you take that dimension and calculate the volume of the whole piece. Like the conical maybe speed map in risk, right?
Okay, yeah, for straight
So-
going, yep.
So I've always used that as my median to then,
Okay, all right, I think I understand what Lee's saying. Let me draw that because that would actually be really helpful, I think. So what Lee is saying is if I have something which is a taper, a straight taper, nice uniform taper. And I know some dimension here, I know some dimension here. I could probably get pretty good if I know that somewhere along here, this is the average dimension. I can use that dimension as the basis for my calculations. Instead of having to put in all the estimated missing volumes and so forth, you could do this. And I think you're right, Lee, that would also work. Yeah. Does everybody understand what Lee was suggesting? Because I think that method, I happen to like doing the geometry. It's fun for me, but it's not fun for everybody, so this is another right now. As a sort of a somewhat related, but not exactly, to this, it reminds me of something that I did in the shop when I was first starting this project. I started with a forklift, section of forklift that I had, and the forklift was tapered. And I knew the weight of the section of forklift that I had, and I knew how much weight I wanted for the project, and I could get, I had enough weight for 2 pieces in that section of tapered forklift. But I needed to cut it so that I had equal volume, not equal length, right? Equal volume. And so I played around with measurements and stuff, got a little frustrated and said, this is silly. And so imagine this section of tapered forklift. I took a piece of 1/4 inch round, I laid it on the bench, set my forklift on there, rolled it back and forth till I found a balance point, drew a chalk mark on it, and cut it.
Yep.
Right? And that wasn't my own idea. I stole that from somebody I saw on YouTube or something, somewhere along the line. But I went, hey, whoever came up with that was a really good idea. I'm stealing that one. But it's very similar to what Lee has just recommended that we do. So yeah, if you're ever dealing with weird shaped pieces and you're trying to get equal volume, find a balance point. The calculations are a pain. So yeah, there's definitely more than one way to get to understanding the volumes that you need in sort of complex shapes. I'll just put in a plug for geometry in the sense that I went and got a full engineering degree with all that calculus and everything. And the only math that I've done for the last 22 years is high school geometry, because I figure out this kind of stuff when we're making parts at work. It's the same math. It's the volume, just like I just described. So that's not to say there's anything wrong with calculus. You need that for certain things. But the geometry is what I ended up landing on for myself. If you asked me to do an integral calculation today, I'd have to go back to the textbook and reteach myself that math. All right, so we have different segments, we've got their volumes, and I had just said before Lee offered his suggestion, how if you do that, you'll be wrong. And the reason you're going to be wrong is because you will be missing some of you'll need more metal than the paper math tells you that you need. That was the problem I ran into when I tried this the first time. My first piece, which was that long skinny one passing around, I didn't allow for certain things, so some of my features came out undersized to what I wanted, and then my shaft length was a little undersized because the stop blocks I was using were a little shorter than 1 inch, and so I had the correct volume there for 1 inch, but when you make it 0.9 instead of 1.0, you end up with extra length in the shaft, which is what happened on that one. But as practice pieces, they were still really, really useful. That's all that they were supposed to be. And from that, I learned that I needed to be allowing for losses of things like the fact that this cone is not going to be a true, perfect, paper math cone. It's going to be a rough forged cone. It's going to require some material to be finished. You might end up forging it a little over length, and you have to trim that back, so you have to allow for that. In these corners, I ended up doing grinding along the way because I ended got the little cold shuts and laps in there. So have to account for that, some of that material having to be removed. The ends bulging out and becoming radius. This one's already been trimmed, but I was mentioning earlier, you have to allow for that. In these corners here, you may have a little bit of grinding to do. So you have to allow a little extra over what the paper tells you you're going to need, but it's still going to give you a good starting point, a minimum amount, and then you add some extra percentage to that for what you're going to have to allow for those other considerations. So that will give you a total weight that you need, and I might have had it on my paper. I'm not sure if it tells what weight I'm shooting for. I think it was around 10.5 pounds. I don't know if I wrote it down on that sheet. So you come up with a total weight. So now you know how much weight you need, but what size stock do you need? Because if you start with the wrong cross section, you will end up not being able to create some of the features that you want. One of the considerations is how are you going to get how are you going to make some of these features that will dictate the size of stock that you're going to need. And the way that I chose to go about doing this project, and this is certainly not the only way to do it, but what we're going to do is we're going to use the side set tools like I showed yesterday, and we are going to side set. The first step is going to be to side set some metal close to the end, and then some metal over here. And the reason for that is because we need to isolate some material to become this spike. And there's some more drawings that I have to show this. Let's see here. Oh, here's my weights. So, okay, here's what I actually ended up estimating for the dimensions and the weights. So I ended up choosing to go with a weight of about 13.5 pounds. We can pass that around. Those are my little calculations that go with the previous drawing. So, one of the dictating features that I have to think about is the dimension of this part of the tool, and specifically how wide this is going to be. So this is my design, this is 1.5 inches wide. So I need this starting material to be at least 1.5 inches wide, or I'm going to struggle to make that dimension later in the project. And I also need to determine how am I going to create these two different masses of material. There's more than one way you can do this. The way that I chose to do it is to side set, and here's a drawing that shows kind of the first step of how that will be done. So we're going to side set. I'll walk this around and then I'll pass it out. But we're going to side set some material. The material on this end will become that flat bladed portion, and the material in the middle will become the spike. Okay? And so you might go, well, how are you going to get that flat bladed thing to be in the correct orientation? All right? Because it's kind of a weird starting approach. I'll pass this around so you can all look at it. But what you're going to end up doing is a second side set later on. So what we'll do is we'll isolate this material, and then later on we'll side set in this plane, and we'll forge it out again. And then we'll have to bend it. And it's this dimension that I'm controlling at 1.5 inches. And so that's one of the kind of the dictating features that determines what I need. So 1.5 inches ends up becoming kind of a minimum cross section for the project. And actually, I started with a little bit more than 1.5 inches because I wanted to have the opportunity to reduce the metal down a little bit refine features, get nice clean corners, things like that. So that pushed me up to 1 3/4 for some starting stock. So if I have now one of my dimensions determined for my starting stock at 1 3/4, I next need to think about the width. And so that width is really dictated by how much material do I need to make this spike, right? And the way I'm going to do that is to isolate material and then draw it out. So I have to have enough metal when I do my side sets that's sticking up above the block that I can pinch on that with the hammer dies and pull that out. If it's too short, I won't be able to pinch on it. Or if it's too short, what will happen is what I was talking about yesterday. You'll end up with an end. If I have a short study projection, and I'm trying to draw this out in this direction, but if I can't get, enough metal under the dies, then when I go to draw this out, it'll come out, but it'll end up coming out, and it'll have a crack kind of down the center of it, right? It'll be kind of horrible looking. I don't want that, so I have to have enough metal in that spot so that I can get a nice wide die bite with big heavy blow so that I can push this metal out and have it bulge out on the end like I did with that motorway bar. So I have to think about how much metal do I need to make that happen. So that's going to be a combination of this dimension here, and also if we were to draw this back, going back into the plane of the page or whiteboard, right? The rest of our wood pieces up above that, right? So again, this is going to have a volume. It's got length, it's got width, it's got height. So we can determine how much volume minimum we need for that by doing the cone calculation. But we know we're going to need more because we're going to have to allow for grinding, and we know that we're going to have enough projecting out to start with so that we can get the dies to grab that and pull that metal out. And so what I decided was that I needed to have metal of something along the lines of, I think it was, what is it? It's like an inch, it's on my sheet, but if I remember right, it's like 1 3/4 in this dimension here, from here down to here. Will be about 1 3/4. It'll probably be a little bit less than that because when we drive those side set tools in, it's going to pull that metal down a little. And that'll end up giving me so when I forge to something like that, then I will have, if this ends up being 1 3/4, then that would leave this dimension at also something about like 1.5 is what I'm shooting for here. Because I want 1.5 in this dimension because of that other feature that I'm trying to make. So these are the things that are going into determining the size of the block, both the thickness and the width of the block. But I start with, once you have thickness and width, and then you have a weight already predetermined at, in this case, like 13.5 pounds, now you can determine the length of the block that you need. That is what we end up with. Yeah.
Would there be any benefit to go online and get what is the weight of a finished bar, commercial bar, that gets you into a neighborhood?
Sure. Yeah. Yeah, you absolutely could do that. If that gave you the weight, like if you had like let's say you wanted to model one off a commercial bar, that would give you the finished weight. You'd still have to have allowances, right? And keep in mind that that weight would be based on the way they made it. And the way I'm making it is, I'm sure, not how a commercial producer would make this, because this is a time-consuming approach. What they would probably do, my approach is designed to kind of illustrate certain forging techniques, calculation methods, and to try to see how close I can come to using the least amount of metal to make the bar. recognizing that I'm gonna end up putting more time into the job, right? If I was interested in making this as fast as possible, we'd make dedicated closed dies and we would pound these out. We'd have a bunch of trim waste, but we would be able to make them quite rapidly, right? But we're going to do it by an open die process, not worry about the time, and focus on a different aspect of the job. So, but you're absolutely right. You can go and see what commercial bar weighs and use that as a rough starting point. For sure. So now we have the block size to start with. If we were to start with a different block size, there'd probably be other block sizes we could start with that would work, especially like if we went with a little bit wider block. That's what this block was forged for. This is a 3.5 inch wide block because I thought that might give me a little bit more advantage in pulling out the metal for that spike. And I'm not worried about so much being able to draw the metal down behind the spike, but I am worried about a different part. Let me see my next surround page. And it might be, let's see, there was another page that was probably going around right now somewhere. Yeah, I see it over there. If you look at the page that's happening to go around right now, and I'll sketch it on the board, when you forge that and you make your first side set, it's out near the end. Oh, and here's another thing. Well, we'll do this here. So when you make this side set near the end of this block, you've got one going over here. So when we do this and then we start to draw this out, we're going to be pounding down here. We want to move this metal out this direction, and then we'll do that. But we're going to have a hard time getting this to bulge evenly on the end because we're only going to be pounding on it from one side, and we're only moving metal on one side. So what's going to happen is as this comes out, it will move out, but it's going to move out more sort of on the top, just like we talked about yesterday with some other shapes. You'll end up with kind of like a double chin sort of a feature here because so much more of the top is moving than the bottom. We actually see the exact same effect on these little tools that I forged yesterday. You can see it right here. You get more metal moving on one side than the other. Yesterday we used that to create this sort of pre-form for a taper on purpose. In today's project, we're not interested in having that feature. What we're concerned about is that if that became too severe, you could actually have a forge lap created in that spot. So we have to watch that as we're forging. If we see that that's progressing too much towards a lap, we can stop and grind that out, okay? The other thing that is a challenge is we can know how much metal we need just for this blade section here, which we're going to get from all of this volume, okay? But we don't actually need all that much metal to make that volume, or to make that part. So we're going to have a bunch of excess in here that we have to account for again, not because we need it, but because if we're starting with a block like this, if I were to only side set the amount of volume I needed just for that blade, that would put my side set really, really close to this edge. Be way over here, like this, okay? And if I try to side set right there, I won't even get this. It'll just lay right over on itself and become a lap, right? Remember I said yesterday about how much metal we have on the end and we want to make a bulge, and I said we really want to have at least, if we're trying to get this sort of geometry on the end, we want this dimension that's under the hammer to be at least 1 times whatever this dimension is. This should be the same or more. right? Well, I started with a block that's 1.75 inches wide and 3.25 inches tall. So I ought to have something like at least 1.75 inches if I'm gonna follow that rule. Well, if I come over here 1.75 inches, I have a huge amount of excess volume that I need, right? Because what we would be doing is we would say, all right, here's my side